So first up, last class, what did we review? What did I say last class was really important? We know. Good, anyone who's comfortable.
Balancing equations.
Balancing equations, very important. What else did we talk about last class?
Nomenclature.
Nomenclature. So there's three major components to stoichiometry. Now remember, stoichiometry is the really weird rule, or sorry, I'm reading what Sangeet wrote, is the really weird thing where you can look at a chemical reaction and you can say, I had this, how much of this should I get? So it's very predictive. It's how we can do lots of math about lots of things involving chemical reactions. And this is where we said we were going from the baby steps of looking at chemicals in isolation, and now we're looking to their interactions and relationships. So it's like we've gone from psychology to sociology. Okay, so we're just shifting from looking at individual atoms to looking at how atoms interact with one another. So that's our focus. So to do that, we have to know what atoms look like. That's the nomenclature part. If I tell you hydrochloric acid, you should be able to create HCl using your naming sheet in the reference packet, right? And then if I say sodium chloride reacts with sodium hydroxide or whatever, like two different compounds, you should be able to write that reaction, do the replacement, and create the products. Once you have the reaction, you should be able to balance it. Now, those are all things we did last semester, all of them. We reviewed them a little bit. We'll be reviewing the writing reactions part more next week when we do the rest of what we're doing today. So the last step of that is once we know what we're talking about, we know how it's interacting with something else, we know how to balance it, as in which proportions things are happening in. The last thing we have to do is actually do the math. So I'm going to make a big assumption today and assume that you remember the first three things, and we are going to focus very heavily on just the math portion today. So just like we broke down the other components, we are laser focusing on this one. Your QC will be more difficult than what we do today because you will have to create the reactions. I am giving you the reactions because I want to focus on the math part because that's the part that's new. And I say new because you'll see why, but it's new. It's not really new, but it's new. Okay. So we're focusing on math. I'm going to review balancing equations really quick because we didn't do as many last time as I would hope. And combustion's like your crazy aunt that shows up to Christmas and she has like a pie like everybody else and looks normal. And then she starts talking and you're like, oh, ugh. Right. And so that's why you crazy. So we're going to talk about a crazy aunt today, just so we get really good at balancing. And then we're going to move into the other part. So we're going to start with this combustion of butane. So using the name wheel to pick who is going to help me. Question number 1 is going to go to Victoria. Victoria. Okay. How are you, Victoria? Good morning. Victoria, are you here?
Is there another Victoria in this class?
I don't think so. Yes, maybe Victoria C, but we can do you too. Right here. You go ahead. All right. What does it mean when I say balance an equation? What process am I describing? What is that?
You make sure that the product and reactants both have the same amount of atoms.
Yes, I love that you used all of the best science words. That made me so happy. So we are going to make sure that all of the products, which are over here, and the reactants, which are over here, have the same amount on both sides. Now, the $1 million question, thank you so much, Victoria. The $1 million question, Corey, why? Why do we do this?
Like balance them?
Yeah, why do we balance? Like I tell you, this is how we balance, and you know what balancing is, but why did some dead white guy like 100 whatever years ago decide that this is what we needed to do?
Because of the law of conservation of mass.
Oh, you even said the whole law title. Oh, that was so good. Oh, I missed you guys. So law of conservation of mass. For the rest of the world who may not remember what that is, can you describe what that means?
Basically you can't make something without like already having that same amount of things.
That's perfect. Yeah. You can't create something or destroy something. We can't like Thanos and nope, you're gone now. And we can't like Houdini pull the rabbit out of the hat, right? That's not a thing. So something doesn't come from nothing and we can't make something into nothing. Everything that has existed will continue to exist. And that's why all like the Target t-shirts are like, we're really all stardust and whatever. That's what they're talking about is the law of conservation of mass, is that the atoms that make you up made something else up before you. Okay. So if we're looking at this, reactants products, we're going to have a balance because of the law of conservation of mass. And that gets very important later. Thank you, Corey, for letting me pick on you with my weirdness. All right, Basil, you're up. Tell me how many of each type of atom I have on the left side.
Okay, so on the reactant side for carbons, there's 4 carbons.
Okay,
There's 10 hydrogens,
beautiful.
and there's 2 oxygens.
All right, you did that so great. Go ahead and give me the products.
Okay, for the products, there's 1 carbon,
Okay,
2 oxygens,
okay.
2 hydrogens.
So there's 2 hydrogens and how many oxygens?
Oh, oh, here there's 2 oxygens. Sorry.
So there's 2 oxygens and CO2. What about this one?
1.
So you add those together and you get
3.
3. There we go. That is one of the most common things you can do. I actually did that to third period yesterday. I was like, there's 3 oxygens, and it took me a second. Like that's something like your brains like to do is skip over that water because you see the O2 and you count and you feel like you're done. So just be aware of the trap, that's a trap that many people have fallen in, including moi. And I have a master's, so that's cool. So just be aware. Okay, be aware that that water always will add the extra, and it's kind of weird. All right. So here's what it looks like. Next up. Trisha, do you remember what order we balance combustion reactions in? There's a specific order I gave you for a very specific reason. It's okay if you don't remember.
I think it's carbon, then hydrogen, and then oxygen.
That is 100% correct. Good job. Next time, say it with more confidence because you were amazing and you had it right. So when we're looking at this, we're looking at CHO. The phrase that my professor taught me that I don't think I mentioned last semester was, you guys have heard the phrase that when you're thinking about something, it said, let me chew on it for a minute. And it's like a phrase meaning that you're thinking. So my professor always said, when you have combustion, you got to chow on it for a minute, like, chew, chow, whatever. They always made it CHO. So you got to chow on it when it's combustion. So we'll start balancing it now. Thank you, Trisha. I'm going to pick on someone else. Ray, balance the carbons for me. Ray, Bope, Banana, Fana, Fofay. Are you here? Ray. Okay, I can't sing. It's really bad. Yeah, you're here. Someone text him and be like, what up, yo?
Hello? Hello?
There you are.
Wait.
What up?
Okay.
All right. Balance carbons for me.
Okay. So there's 4 carbons, 1 carbon. Wouldn't you just multiply CO2 by 4?
Yes, and when we say multiply by, we write the number out front. What is the mathematical or scientific name for this number out front?
Coefficient.
Coefficient. So there's a coefficient of 4 on carbon dioxide to result in the balancing of carbon. So can you tell me how this 4 affects the values of each atom? How many of each one there are?
It multiplies the carbons by 4, so it's 4, and then it multiplies the oxygens by 4, so it's 8.
Well, there's 8 here, and then there's what?
Oh, there's 8 there, and then there's 1 on the water, so it's 9.
Yep. See, told you guys, it's very common to miss that one. Don't ignore water, right? Okay. So that was perfect. Thank you so much. Next up, Lucas, balance hydrogen for me. Balance hydrogen for me.
Okay, so you would keep the 10 hydrogens on the left side on the reactant side, and on the product side, you would put a 5 in front of the H2O.
And what is that 5 called?
Starts
with the C.
Coefficient.
There we go. Coefficient. So that gives me 10 hydrogens. What else does that change?
That gives you 5 more oxygens, so that's 14.
Well, 4 times 2 is 8.
Oh yeah, sorry.
It's 4 more 'cause
Uh,
there's one here. Yeah. So that's a common mental math for people, is that there's already 1, there's 4 more than there was, would be 9 plus 4 is 13. Or you can do the
Yeah.
4 times 2 is 8 plus the 1 is 9. Was that plus the 5 is 13. So that's 13 there. Awesome. All right, good job. So now, so far, Crazy Aunt Karen, or whatever her name is, we're gonna say Karen because it seems relevant, right? Crazy Aunt Karen has shown up. She had her food. She brought her pie. She knocked on the door. She came in, she sat down, and she seems real normal. And now she started talking, and she seems a little crazy. Why do I say that, Samir? Why'd she just turn into Crazy Aunt Karen?
Do you say my name?
I did. Why is it, what do I do now? This is the difficult part because
All right. So here's the predicament we're facing. We're facing so on the left side we have O2 and it goes up in even increments by 2. But on the right side it's odd. So you have to make the right side even. So the way I would go about it is fix the odd problem with it. So it's got 5 oxygen, make it 10 oxygen, because you still have to keep the same, like, in terms of 10 hydrogen. Like, do you understand?
I understand what you're trying to say. So I'm going to give you a postulate. So what are you saying we multiply by 5? What you said a 5 number there. Can you walk me through what you meant?
Okay, so you have 5 oxygen on the right side. So
You mean 5 waters?
well, yeah, five water with the oxygen inside of it. And so you have to make it 10 because you want to keep that 10 hydrogen. You want to keep it as a multiple of 10. So you have to make it like 20. Like, am I saying this right?
You are doing it the hard way with great mental math skills. So hella impressed. There's an easier way to come to the exact same conclusion. But again, hella impressed with your mental math. So good job for you, friend. Yes, you saw the proportions of the ratios need to stay the same. And you said you need to make this 10. So I'm going to tell everyone else so they can follow the mental math gymnastics you just did and appreciate you a little more. Okay. So here, if I were to do this the way we have been, right? 2 goes into 10 5 times, multiplied by 5. So it's like 2 goes into 13 times. So that's 13 halves. Okay. So here's where I'm going to pause and we're going to put a pin in what we are doing. And I'm going to tell you, remember when I tell you it's really easy for me to tell if you look something up in Google because you don't know what you don't know, right? It's like when your friend tries to pretend they play the same video game you do, but then they don't know anything about it. And you're like, bro, just tell me, it's fine, right? Like, there's times. So when you're doing this reaction and you Google combustion of butane, there are going to be a number, and I mean a large number of sites that will tell you this is the balanced reaction. Okay. 1, 13 halves, 4, 5. This is not for you. So this is not something you are at yet. We only do this when we are doing heat of formation, bond enthalpy, heat of summation, Hess law, thermodynamics. And the fact that you have no clue what I just said means it's not you yet. When you come to IB next year, you will totally be doing all of those fun things with me, and I'll show you all the cool ways, and we'll make jet fuel and all this other stuff, and you'll love it. But right now, that's not you. So you are not allowed to use fractions in your chemical reactions ever. So the easiest way to get rid of a half is to double it, which is the same as making this 5 into a 10, which is where you did the mental gymnastics of doing all the proportions in your head. You did all of this in your head versus calculating all of this after you double it. So you did it backwards the hard way, which is why I said hella impressed. But if you take this, the easy way to get rid of a half is just to double everything. So what we do is you would take this whole thing and multiply every single thing by 2. So now we have 2 butanes, 13 oxygens, 8 carbon dioxides, and 10 waters. If you were to do the math on that, 4 times 2 gives me 8 carbons, 20 hydrogens, because you needed to keep it in the multiple of 10, which again, this is where he said that multiple of 10 thing. And then that 2 becomes, well, 13 halves really becomes 13. And then here you have, I'm sorry, 2 times 13 is yeah. And then you have 26. What am I doing? Why did no one call me out on that? What the heck? 13 times 2 is 26. Be better, guys. Call me out. Okay. The next one, 8 times C is 8. 8 times 2 is 16, right? But we also have the 10 from over here, which gives us 26 oxygens, which is what we wanted. And then we have 10 times 2, which is 20. So now all of these numbers match because we doubled it. So if you get stuck with an odd number of oxygens, just double everything. Okay, this is why, again, crazy Aunt Karen. It seems normal until you get to the end and you're like, oh no, no, you're not allowed to come back here, right? So I just wanted to give you guys, this is the hardest type of balancing there is, truly. The only other pro tip I want to give you to balancing today is to remember that if you are balancing a double replacement or a single replacement with polyatomic ions, you can balance by the polyatomic ion. You don't have to split those guys up when you count because they always have to be together anyway, right? So those are the 2 pro tips. When you have combustion and you get stuck, double it. When you have the polyatomic ions, count by the ions, okay? Scale of 1 to 10, how we feel about that in the chat. Privately, publicly, however you want to tell me, just let me know. Give me those digits. 1 to 10. Okay, looking pretty good. All right, we're gonna bump it up a notch. You ready? So this is where we're gonna start dancing with concepts that we are going to do today. And I'm gonna show you how you've already known this since 3rd grade, because I literally did similar math with my 3rd grade son. Okay, so this next thing is not new. We're just gonna phrase it in a new way. Everybody tracking? Okay, so this is that balanced reaction. This is butane. I color coded it for you because it's pretty, right? No, that's actually helpful too, because I'm gonna put everything in words. But now we're gonna look at this. We understand the relationships in the reaction. Every single type of compound here is related to the other compound in the reaction. Butane has a complement reactant of oxygen, right? That's the other reactant. When we consume oxygen, one of the things we produce is carbon dioxide. When I've produced water, I know I've consumed butane. Like, you can go and mentally weave yourself back and forth through this reaction, okay? So first question, if I consume 2 moles of butane, how many moles of water were produced? Shanmathi, give me that one.
Do I work it out?
So try to work it out just by looking at the reaction. I said I consume 2 moles of butane. Okay, this is butane. How many moles of water are produced?
Would it be 10?
It would be 10. How did you know?
Because the coefficient in front of the water is 10.
Yeah, so for every 2 butane in this reaction, I know that I end up with 10 waters, because those are the coefficients that we just did the math to practice. So remember when I talked about law of conservation of mass? I'm going to make you explain it because it's really important later. This is later. We're going to unpin it and we're going to put it back in the problem. Okay, so law of conservation of mass matters here because every atom that has existed continues to exist, and every reaction happens atom to atom. It does not happen mass to mass. It would be like trying to count animals in a zoo by their pounds. So you would think that there's way more elephants than monkeys, but the opposite is probably true, right? Because monkeys are smaller and elephants are bigger and they're harder to maintain, etc. You can't compare things by mass because things are different sizes. But if I told you, hey, there's 5 elephants and 15 monkeys, you would know exactly what you're dealing with in terms of the zoo ratio of how many things I'm going to experience in that zoo. Same thing here. We have to count by the mole, by the atom. So these numbers represent atoms or groups of atoms that we have decided are groups, like when you count by dozens, or when you count by pairs, or when you count by triplets, or whatever. We are counting by moles. It's the way that we chemists know that we are doing reactions atom to atom, molecule to molecule. Scale of 1 to 10, how we're tracking there. I know it's a divergent thing, but it's really important you get that delineation. Good. Okay. We're tracking above a 5 average. That's pretty dang good. If you're not at that 5 average, that's okay too, because we are still in the beginning of class. You'll get it more later. Second question. Dun, 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 dun. Madison, if I produce 8 moles of carbon dioxide, how many moles of oxygen did I consume?
Um, 13,
Yes. How did you know?
because there's 8 on the coefficient of carbon dioxide is 8.
Yep.
And
So yep, the coefficient is 8. So that means that this relationship is not altered in any way. So that's how you got the 13 oxygen. Love it. Good job. Beautiful big brain moments. Love it. Last question. Going to Sneha. You ready? If I consume 1 mole of butane, how many moles of carbon dioxide are produced?
Would it be 4?
It would. How did you know?
Because you would divide the 2 in half.
Yep. So we had 2 moles of butane, right? So how do we get to 1 mole of butane? We divide it by 2. So if we're looking at carbon dioxide, we had 8 moles of carbon dioxide. How do we do that? We divide by 2. So we end up with 4. So it's a direct proportion. And this is why I said that even though I didn't tell you that's what you needed to do, you automatically knew it in your brain space because you're smart and you understand things and you're good at this. So you literally have every single math and science skill to do stoichiometry right now. Okay, every single one. All we have to do together is to stitch them together in the correct order. You already know this. So I'm going to say again, you already know this. It's just a matter of sequencing things in the right order. And that's my job, is to show you how to do that. But you have to say again in your brain space, I already know how to do this. Okay, confidence abounds. You got this. So with that being said, we are going to move on to Canvas. I want you to go, everybody go into Canvas. You're going to do this with me because I'm going to demonstrate how you're going to do the group activity. And this is another one of those days that if you do well in your group activity, you are going to be allowed to leave. So you don't have to stay the entire time. Okay. You just have to stay until you have demonstrated mastery of this concept. Okay. So that is the idea. So everyone go to Canvas. Your Canvas, see how many things, so many courses. Oh my gosh. Okay. So modules, and you are going to come down and you see where it says in practice, AKA not graded, there is a stoichiometry. I can say words, stoichiometry introduction in class activity. Okay. These are what we did last class. They're there for you to practice if you need help. This is this class. So click on that guy, and then you're going to click on the link here. When you do that, it's going to say, hey, do you want to make a copy of your lesson? And you're going to say, yes, I do, because I want to follow along with Miss Longley like she asked me to. So you're going to click that. Beautiful. And you're going to get here. Okay. And this is where we're going to be working from for the rest of the day. All right. So I'm going to give you guys a second to pull that up. Give me a thumbs up in the chat or an okay or I'm good or whatever. So I know you're ready, and I'm going to wait till I see a lot of them and then I'll start talking. But I want to make sure you have the resource open before I start speaking. Okay. See lots of thumbs up. Okay. I see lots of thumbs up, so we're going to move ahead. All right. So for stoichiometry, you'll see this map every time you Google it. I actually think this map is very obscene and makes it look more complicated than it is. So I want you to listen with your brain space. Okay. Focus here. So when you're doing stoichiometry, assuming you already have the reaction and it's already balanced. So you've created the reaction if necessary, you've balanced it, and all that's happening. We're assuming we're starting at the balanced equation. Every time you have a chemistry problem from here on out, the first thing you do is go, is my reaction balanced? If it's yes, move on. If it's not, you balance it before you do anything else. Capiche? Yep. Okay. So we have the balanced reaction. Step 1, convert to moles. So the first step is to convert to moles. And before you do anything else, you need to convert to moles. And when you convert to moles, you'll be able to do anything else. So we're going to convert to moles. So let's see. Where did my name wheel go? Where did it go? All right. Gus, what's the first step?
Morning, Miss Longley.
Good
I
morning.
regret to inform that I am not sure.
Okay, guys, someone spacebar, help him out. What's the first step?
Convert to moles.
Convert to moles. So what's the first step, Gus?
Convert to moles.
And before you do
Thank you,
step
Darshan.
two, yeah, before you do step 2, what are you gonna do?
Convert to moles.
Yes, I know I'm saying it over and over, but you guys would be so amazed at how many times people forget that step. Like, I will scream it, I will yell it, convert to moles. Moles are your bridge between one atom and another because we have to compare them at the atom to atom level. You must convert to moles. If you already have moles, you get to skip that step, and that's beautiful. Just like if you already have a balanced reaction, you can skip that step, but you can't skip it until you're sure. Okay, so convert to moles. So if you look at this confusing map, everything you see here is literally just saying, hey, if they give you mass, convert to moles. Hey, guess what? If they give you particles, convert to moles. And guess what? If they gave you liters, think what you need to do? Convert to moles. So it's literally just saying convert to moles in a really confusing way. Okay, but you'll see this everywhere on the interwebs. So I just want to make sure you saw it. Okay. The second step is to compare moles. Second step is to compare moles. So that's what we just did in the PowerPoint when I was like, if I have 2 moles of butane, how much water? Like, that's literally exactly all that means. You've already done that step. You learned step 2. That was the new thing of the day, and you did it. And it wasn't even really a new thing. It was an old thing in a new way. So compare moles. The last step is to convert to what you need. Okay. So let's see. Normally, if we were in class, I'd make you guys shout this back at me a lot, but instead I'm just going to be obnoxious and ask them all again. So Darshan, give me all 3 steps. What are the 3 steps?
Convert to moles is the first step. Then
Okay.
compare moles. And
Okay.
then, go to what you're trying to find, like the mass particles.
Yeah,
volume.
convert to desired, convert to what you want, whatever. Beautiful. Akshar, what are the 3 steps of stoichiometry?
Balance equation, convert to moles.
Balance equation, convert to moles. Okay, what's the next one?
And whatever they have to do, like convert to mass, the grams, or
Yeah, so you convert to, so if you're given something, you convert to moles. So you're here, then you compare moles, right? And then you convert to desired. So what's step 1?
balance.
The balancing is before this. So balancing is what you have to do before you can start.
You convert to moles, and
Yep,
then
convert to moles, and then you
use the molar ratio.
molar ratio. So you compare moles. So you just look at the chemical reaction just like we did on the slide. And then what's the third step?
Moles of unknown.
Yeah, moles to whatever you want, right? To the desired thing. Renee, give me all 3 steps of stoichiometry.
First you convert to moles, then you compare moles, and then you convert to what you need.
Awesome. And last but not least, Kai, give me all 3 steps of stoichiometry. Then I promise we'll move on.
Convert to moles, and then compare moles, and then convert out of moles.
Yes. So if you forget what to do, stop, drop, and remember your 3 steps, right? Convert to moles, compare moles, moles to what you need. Okay. So that's all we're doing. I'm going to show you how to use this thing. So if you go to slide, I think it's 3 or 4. Wow, the view is really bad. Why is this doing this to me? Hold on. Ha, better. I win. All right. So when you have this, this is what you're going to be working in the rest of the day. So again, I've already made the assumption that you, 1, can write the chemical names and put them in reactants and products, predicting the reaction. I've assumed that you know how to balance it. I've also assumed that you know how to calculate molar mass. So I've just done all that stuff for you so we can focus on just the 3 steps of converting to moles, moles to moles, moles to what we want. So step 1, we got to figure out, well, first we're going to identify our information. So we're going to go through and label our information and figure all that out. So who's going to help me? Jessica, what is this question asking me for? What is my unknown?
How many grams of Al2O3 are needed to produce 34.5 liters of O2 gas at STP?
Yep. So the unknown is how many grams. That is the question, right? It's not to be or not to be. It's how many grams. So the question is how many grams of aluminum oxide. Okay. You said the given. So I'm going to go ahead. What they gave us was 34.5 liters of oxygen. Now I'm going to do one of my weird reminders again. Do you remember when I screamed from the rooftops in dimensional analysis to always put the compound or element inside the railroad tracks? Because there's going to be a point in time where we are going to have multiple compounds in the same railroad track and you need to keep them straight. The time is now on this slide right here. We've made it 3 months of like buildup and we're here and it's going to be kind of anticlimactic, but it's okay. This is it. This is when you do it. Make sure you put the element and the unit or your number will be considered naked. It is not fully dressed or appropriate for public, okay? It's like forgetting your pants. You don't do that. Don't forget your pants, okay? So 35 at 4.5 liters is the given, and therefore that is what I'm starting my reaction with. Okay, that was long-winded, but hopefully you get it. Second, okay, I'm gonna say this wrong again. I know I said it 2 ways that were wrong, and then you said it the third way. Is it was Minahel, see, that's bad. I know it's bad. As soon as I said it, I know it's bad. Tell me how to say it again.
It's Minahil.
Minahil. Emphasis in the middle. Okay. I was like, Minahil. Okay. Minahil. I got it. All right. So what do I do now? I have liters. What's step 1?
Convert to moles.
Convert to moles. How do I do that? Which one of these do I need?
The one with the liters on the bottom.
Yes. How did you know liters needed to be on the bottom?
Because liters was on the top, so then you put it on the bottom.
Yes, because units math just like numbers math. And when something appears on both sides of a fraction bar, they disappear, right? So liters was canceled. I'm left with moles of oxygen, which I was trying to convert to moles of oxygen, so I win. So now we're going to go to step 2 and I'm going to pick on someone else. Okay, so hiccups. All right, Sneha, tell me the next step. What's step 2?
Then you have to make sure that the mole goes on the bottom because it pairs up.
Yeah, so step 1, we converted to moles. What's step 2? What did we say step 2 was?
You have to compare.
So we're comparing which moles to which moles because we're going to have moles on both sides of it. So which moles goes on the bottom and which moles goes on the top?
I'm not sure.
Okay, so this is where I said we already know how to do this and we're just going to redefine it. So let me help you laser focus it here. So we have moles of what compound right now in our railroad?
That's oxygen.
So we have moles of oxygen on the top. So now which one needs to be on the bottom?
Would also be oxygen.
Yes. How many moles? How do I tell how many moles?
I'm not sure. Oh, it would be 3.
Yep, because it's from the chemical reaction. So this is why we have to have it balanced. Our step 2, the step that is the thing that defines stoichiometry, comparing one element to another, has to happen at the molar ratio, which you can only get from the chemical reaction. Okay, so that's where the chemical reaction ties into the math. Okay, so if I have 3 moles of oxygen on the bottom, which one would you have put on top?
So if you have 3 moles of oxygen on the bottom, then you would.
What is it asking me for? Where am I trying to go? What's my destination?
How many grams of Al2O3?
So which compound needs to have the moles on the top?
Al2O3.
Yep, so that 2 moles of Al2O3. Because remember, we can't go directly from liters to grams. So we're using the moles like a bridge to get from one place to the other. We have moles of O2 on the bottom, moles of Al2O3 on the top. Now they've canceled, right? So now I'm left with moles of Al2O3, but we know that's not what the question asked us for. So now we have to do step 3, which is why I said this over and over. Charles, go ahead and do step 3 for me. What is step 3? And then do it.
Step 3 is going to be converting to moles.
Well, step 2 is we're converting away from moles.
Or away from moles, yeah, to grams. My bad.
You're good. So how do I do that?
you would have the moles on top and bottom, moles on bottom, and Avogadro's number on top.
So
Sorry.
Avogadro's number would give me the number of molecules. Where do I find molar? Where do I find molar mass?
In the periodic table.
Yes, and I would add it all up. I did that for you here because I wanted you guys
Thank
to focus.
God.
Eventually later you won't. But guys, if you forgot how to do molar mass, if you remember the weird joke where it's a pain in the mass to go look at the periodic table, right? Because you got to go look it up. So that's the joke, like molar mass, pain in the mass, go to the table. So you got to add them all up from the table. So you would have done 2 times aluminum plus 3 times oxygen. You would have gotten 1 to 1.96 grams, and you would have successfully done that because you're amazing. And then you would be done setting it up. What's the last thing I have to do now?
Multiply across.
Yep, multiply across. So you guys go ahead and do that. Put it in your calculator. But remember, what are calculators?
Pretty stupid.
They're stupid. They're the worst. So be careful because calculators are tricky and they're evil. So everyone try to put this in your calculator and then put in the chat what you get as your answer. Wait until I see a few answers. You can hit me up privately. Okay, so I see a lot of people doing this in the chat. I went ahead and wrote this here. So when you put this in the calculator, because most of you have seen the correct answers, so you pretend that the lines are parentheses. So it'd be like open, close, and now it just looks like a bunch of fractions you're multiplying together. So to do that, I would do open 34.5 close, open 1 over 22.4 close, open 2 over 3 close, open 101.96 over 1. Yes, you don't have to write the over 1, but the habit of mine is I always put it the way I see it, so I don't have to remember. And when you do that, you should get something in the ballpark of 104.96. So I'm done, guys. I'm done. I did the thing. I stoichiometried all over this chemistry class. We are good to go. Yes? No? Am I done?
No, you still need the units and
the units. Okay, so let's check and make sure we got the right unit. So we knew we were supposed to have grams of Al2O3. That was our goal. So let's go. This is what I call the factor label method or the unit checking method to make sure you do everything in chemistry right. I didn't memorize 90.9% of calculus, like the calculations in chemistry. I just looked at the units of the answer and the units of what I was given and then did the math that way. So you can cheat if you know your units, and that's not really cheating, it's logic, but it's cool. So if you have liters of oxygen on the top, it cancels with liters of oxygen on the bottom. Moles of O2 on the top cancels with this moles of O2 on the bottom. Moles of Al2O3 cancels, moles of Al2O3 cancels. I'm left with grams of Al2O3. So I must have set this up correctly because grams of Al2O3 was on the top. So this is going to be 104.96 grams of Al2O3. Am I done now?
No, we need to look at significant figures.
Ah, awesome. So how many sig figs was I given?
3.
So this has 3 sig figs. Conversions do not count towards sig figs because they are exact numbers. Exact numbers don't count. So we don't use this for sig figs. We won't use this for sig figs. This one has 5 sig figs. So how many sig figs do I need to keep? Anyone?
3.
So I start at the first non-zero number and I count 1, 2, 3. So this is where I'm ending and I'm rounding back. So I need 105 grams of Al2O3. Boom. Okay. I spent more time on that because I wanted to make sure you saw exactly how this worked. Now, as you go through these slides, you're going to get less and less support. The numbers will be more and more broken apart. You'll have to calculate more things, but it's a slow release of that support pressure, and you're gonna have lots of time to practice. So here's how it's gonna work, okay? You are going to finish this slide deck in breakout rooms. I'm gonna let you select your breakout room. When you are finished, you are going to appoint or throw under the bus one human, only one human in your group to come back to the main room, share their screen, and let me check the answers. If the answers are correct, everybody will be free to go. If the answer is not correct, everybody will rework the problems together. Does that make sense? So in the breakout room, what are you doing? Bob, what's your goal in the breakout room?
To finish the rest of these slides and work together to do them.
Yes, and then let me see. Izzy, when you're done, if your group is done, what do you do now?
Have you check it, and then if it's wrong, we have to work it out again.
Yes, so you have one person in your group come check it, and if it's wrong, you'll work it out again. If it's right, everyone will be free to go, okay? Are there any questions on anything before I open up your groups? Anything at all? Okay. I have 5 breakout rooms. You can choose your room. If you are not able to choose a room, you can put in the chat which room you would like me to put you in, okay? Okay. Room 5 for, okay, hold on. Oh wait, is the room not open? There, you guys should have been able to go. Why is that not working? That's so sad. I'm so sorry.